to model various aspects of the role well. And I think this workshop is to look at various different examples of how this has been done along in particular these four tracks reflect very topical issues: dynamical systems and networks, AI and cognition, causality, systems biology, and look at how category theory can not only be used to describe these things, but also how we can, what are the common themes across these models and how we can use it to integrate scientific practice. So there's this certain culture that exists among us as researchers, and the idea is to try and bring all these people together and start forming a concrete community. You'll hear later this week how we also have a journal in the works, and that this workshop we intend to continue at least next year in Oxford and hopefully many years after that. So I guess one thing that has been mentioned already is the school last week, and part of forming a community is having good ways to sustain the community, to bring new people in. So I'd like to just say a few words. If you were at the school last week, particularly the students, please put your hands up and just make yourselves known. So in the school last week we had similarly 4 tracks led by John Byers, Martha Lewis, Alex Kissinger, and Pavel Sobochinsky, who unfortunately couldn't stay this week.
Your substitute Pavel this week.
Good.
You'll see the result on Friday. It'll sort of be this long and rather patchy. And yeah, so the students are here. I encourage you to talk to them. I encourage the students to talk to you all and to really make connections. Okay. Anything else before we go into the schedule? Okay. So let's look at the schedule. You'll see 2 talks today, each of an hour, and in these sort of mysterious forms of discussion of the format. So there's plenary discussion, small group discussion, and just plain old discussion. You should consider the latter two the same. So small group discussion and discussion are the same, and this is sort of what Josh is organizing over there. Plenary discussion will happen right after the morning lecture, and that'll be just 15 minutes for us as a group to raise any questions brought up on the theme of the day, particularly pertaining to the opening lecture, and just to set the stage for things we want to think about. The latter two, small group discussion and discussion, also small group discussion, will be a chance for you to break out into small groups of at least one group, not well. The largest size of the second largest group is 14 by room size, but we expect the discussion to be a bit smaller now. We expect sort of 4 to 5 discussions at each section, and we hope that you will propose topics, say just by writing something up there. If you write your topic up first, you get the larger room. Hopefully that's the So today,
I should say the very first small group discussion, just go to your office and talk to your office mates.
Yeah.
I think we decided to do this to facilitate a bit of mixing, so you don't just all find your buddies and talk about the same old things. If you're in a small office, so like 3 or fewer people, then invade another office forcefully. But then after that, we'll do this more topic-driven thing where you're kind of free to go where you like.
So the idea is that at any point, if we think of any topic that's kind of on topic that we want to discuss, we just write it on the board.
Yeah.
Is that what you're saying?
So there'll be a bit of a moment to do that during the short plenary discussion after these talks, but also any time during any time you can write something.
Right. So anything in applied category theory.
Yeah.
Yes. Try to stick kind of to the themes of the day, but we don't have to be too strict on it.
Mr. Bob, he's to instrumental organizing with that, and Nina too. But on that note, perhaps we'll
so we'll be, if you have discussion ideas, please do feel free to write them down on the board, and we'll sort of, the organizers will keep track of them over each day. But we'll also have a kind of, I guess, a record online at the URL over there. So there's a group Google Doc which will be organizing all the times, stating the exact topics, and then recording that so that sort of you can come back to it the day after and the day after and sort of see what exactly happened.
So,
Cutting enough to put his name down.
I'm a disorganizer. I want to create chaos, just come talk to me.
If there's nothing else, I guess we should kick the topic.
yeah, I guess what Josh mentioned is that we also try and keep notes of the discussions, but in particular, a list of sort of a topic title for when you talk about it and list of names is helpful just so we can think about what else is happening during this workshop and some fine through it if you're interested. And we'll also mention that these talks are being recorded.
And live streamed.
In 2 different ways. And live streamed. Wow. And
Where are they being live streamed?
If you go to the Statebox website and then /events, I embedded the thing there.
Okay, cool.
So and that's just a YouTube stream.
okay, and I don't know where the talks will be found after this, but
Also on YouTube, I'll have them. They're like instantly archived after the recording.
okay, cool. On that note, Fabio.
We'll start with Fabio Zanasi.
Yeah. Okay. Very good. Thanks, first of all, for inviting me, and it's a pleasure to open such an exciting week. What I'm gonna give you today is an overview of a work that me and Bart have been developing in the last couple of years, and the idea is that structured as follows. So in the first half, so roughly 30 minutes, I will give you a view about the basic approach, and then Bart will step in and give you some chosen more advanced and those piece of works. And if you want to have, so there are a few papers on this that I'm going to show you, but if you want, let's say, a general reference with also pointers to more specific papers, there is an archive link in the first slide. So what this is about, this is a categorical approach to the spirit is to try to give which the principles that we all got to like about categorical semantics, so in particular compositionality, typing, and an heavy use of equational reasoning. And our approach in doing what people language semantics. You see that our perspectives about Bayesian reasoning will be things like states, predicates, state and predicate transformers. So they are things that are very familiar to computer scientists. And one of the side effects of this is that somehow we hope Bayesian reasoning in this way is also the semantics of what's going on in a calculation in Bayesian reasoning is made more transparent also to people coming from computer science. At least that's how it worked for us. But more in general, the For instance, this notation is probably familiar to you. This is the probability of t, and this is the probability of t given s. Okay? The idea of our work is to try to revise this language, make it richer, flexible, expand it, and give it a clear semantics in categorical terms. So how are we going to do it? As I said, our approach is inspired by programming language semantics. So first of all, we have the notion of state. What we call a state is simply, for now, a probability distribution over a sample set X. So D of X is the set of probability distributions over X, and this omega is just an element of it. Then we have a notion of predicate. A predicate is a function. A predicate on X is a function from a set X to 0, 1. So this you can think of as an observation, a measurement, or a fuzzy event. So it's a fuzzy event. It's fuzzy because the elements in X are not simply mapped to 0, 1, or false, as is typically the case with Bayesian reasoning, but they be mapped in any value in the interval. Then we have the machinery for updating knowledge about the network, and this is conditioning. So conditioning is an operation that involves a state and a predicate. And you can think of it as a revision due to some observation. Then we have what I would say is the truly new ingredient in the framework, which is the notion of a channel. So a channel is going to be a function from a sample set X to the set of distributions over a different set Y. And you can think of it as a sort of change of pace for my observations. And what this means in practice, the way we are going to use these channels is they will play a dual role. So they can either be state transformers, meaning I can apply a channel to a state on X to get a state on Y with this notation. And they can be predicate transformers. Namely, if I have a predicate on Y, I can transform it with this notation into a predicate on X. So notice here that whereas state transformers work forward from X to Y, predicate transformers, they work backwards from Y to X. So this is really an analogy with programming language semantics, where programs may be given in terms of transformers, which go forward from a certain configuration to another one, which is a backward semantics. You go from post conditions, for instance, to a win. This is really an analogy to that. Another thing to observe before, so of course, right now I didn't define yet how these things are completely defined. Now I'm just giving guidelines, but let me just say one more thing. So what is there is another main difference with respect to standard Bayesian probability to notice. Usually in standard Bayesian probability, conditioning is an homogeneous operation. It condition an event over another event. Okay, so you have two events. Here we do a revision of this operation in which the two entities that are involved in the computation, they are of different kind. No, is a state and a predicate. Important between a state of affairs, and the observation of something else that you wanna include in your state to update it. And even though states and predicates, they look very much alike, they're actually different. And this difference has a conceptual value. So a state has to sum up to 1. Okay, it associates probabilities to elements of X, but they all have to sum up to 1. So this is like saying it has to be a coherent picture of reality, if you like. It has to be complete. Instead, a predicate just associates, still associates value between 0 and 1 to elements of X, but it does so in a way that doesn't need to sum up to 1. So this means, for instance, I can assign to x1 0.5 and to x2 0.7. So the idea is that a predicate is not something which is grounded in reality. It's just a piece of information that you get. It might be incomplete, meaning it may not add up to 1. It might be incoherent. Okay, it may add up to more than 1. So these have really different status, and in conditioning, you put them together, but you keep them conceptually separated. Okay, and one can make a few examples taken from the literature where making this distinction really pays off. Namely, if you treat things with types, you really see much clearly what's going on. You can find a developed example of this kind in the paper I put on the archive. I cannot go too much into detail about this now for time reasons. Now let me get to the categorical meaning of all of this. Indeed, even though we gave things of a different type, if you look about them in a certain category, they actually are homogeneously treated as just arrows of that category. So the category of interest here is the Kleisli category for the distribution monad. So this is the category with notation Kleisli of D, where the objects are just sets and for arrows. So an arrow from X to Y, for which we use this notation with the little dots, is just an arrow from a function from X to D of Y in set. Okay, so in fact it's a channel. This is what an arrow in this category is. And if X and Y are finite, you can conveniently think of this as just a stochastic matrix, meaning is a matrix where I have as many columns as the elements of X, I have as many rows as the elements of Y, and all the columns have to add up to 1. And when you think about such an arrow as a matrix, you can also think about the composition of two of these arrows as matrix multiplication. So this is the category we are going to work in. And our primitives, they are all arrows of a certain kind in this category. So a state, for instance, is an arrow from 1 to X, because an arrow from 1 to X is simply a function from 1 to D of X. So it's a function that picks an element of the set D of X. Similarly for predicates, predicates is an arrow from X to 2, meaning is a function from X to D of 2, which is isomorphic to the interval 0, 1. And a channel, as I said, is just a generic arrow of the category. Now, given this interpretation, we can immediately give a sense to this observation that we can use channel as states or as predicate transformers. Indeed, suppose I have a state on X, omega, then I can post-compose a channel, F, and I get a state over Y. Okay? So the transformation is from a state over X to a state over Y. And it's just defined by post-composition. Similarly, if I have now a predicate, I can pre-compose a channel, and the precomposition brings me from a predicate over Y to a predicate over X. So the predicate transformations works by precomposition. And you see here also why one works forward and the other works backwards. Okay? And once you have the categorical machinery at work, you can also define other interesting notions. For instance, you can define what it means, the validity of a predicate in a state, simply as the composition of that state with that predicate. Of course, this only makes sense if the predicate and the state are on the same sample set X. And this altogether will select a value between 0 and 1. So this is the validity, for instance. Okay. So this is what we're going to use to model inference in a Bayesian network. Before moving to that, let me just give you a glimpse of the more general picture. So the payoff for reasoning with categorical semantics is that we can try to transfer the same notions to other categories. And the good news is that this works fairly well. Namely, if instead of Kleisli of D, you consider the Kleisli category for the G monad, for instance, you obtain a similar picture but for continuous probability. Okay, states are probability measures, predicates are measurable functions to 0, 1. And you can also have a quantum case where you reason in the opposite of the category of von Neumann algebras. And in this case, states are quantum states. So this is also where the terminology state comes from. And predicates are so-called effects. So in particular, measurements are a certain kind of predicate. So I won't go into that, but it's just good to know that this has a certain generality. Okay, so we have this toolbox. We want to apply it to Bayesian networks. The next observation is, how do we reconcile Bayesian networks with this toolbox? So what we do is to interpret a Bayesian network as an arrow in the Kleisli category as well. How does this work? For instance, if we focus on a single node, that is this node, this is an arrow of the Kleisli category of this kind. So you see that the target, so everything here is a 2-element set. We just give different names to the elements because they mean different things. So the target here is a 2-element set whose elements we think of as the event of a disease and the negation of the event of the disease. So the event, not the disease. And the source is the Cartesian product of this set of the event genetic relative to its negation and environmental factors and its negation. In general, you can write such an arrow for many nodes. You just put as target this a 2-element set, and as source as many copies of the 2-element set as many are the predecessors of the node, the parents. How do you define this? This is, and being an arrow in Kleisli has to be a stochastic matrix, so it associates 20 elements in here. There are 4 of them, a probability distribution over this set. So you see we use this cat notation analogy with quantum states to write down probability distributions. And the way we define this is just following what the table says. So for instance, the table says that with G and E we have to associate 90%. So with G and E we associate 90% to D and the rest to the bottom. And the other lines, they just follow the definition. So I hope this convinces you that you can perform the same thing for all the nodes. Just a bit of notation. These 2-element sets, they will soon become a bit too clumsy to write down, so we just use this notation. We use 2 with a little G, E, or D, meaning this is the type of the elements inside. And this is just to remind you that the Cartesian product is a definition on objects of a monoidal product in the category we're working in class of D. So this is a monoidal category. And because it's a monoidal category, we can use both sequential and parallel composition to put together these definitions of the single nodes. And we obtain an arrow which represents the whole network. So in this arrow, we have, you see, G and E are channels representing the single nodes here, the priors. Then we have D representing the disease. We have a copy, okay, which copies the domain 2 of D. And from this, it departs 2 arrows, T for positive test and S for symptoms. And this whole thing completely captures our Bayesian network. So perhaps this is more enlightening if I write it down as a string diagram. And the nice thing you observe is that the string diagram actually looks very much like the original network. In fact, we could go further and define Bayesian networks as a certain kind of string diagrams in our Kleisli category. And this kind of observation will become useful later where we're going to manipulate these string diagrams for the purpose of modeling Bayesian learning. So this will be also the subject of the second part, one of the subjects of the second part on which Bart is going to talk about. Okay, so how do we now perform inference? So we have laid down our toolbox in Kleisli. We have interpreted Bayesian networks as well in Kleisli, and now we compute in this category two inference questions. So the nice thing with respect to the traditional way this is done is that thanks to these state and predicate transformers, the computation will have some sort of dynamical flavor. So for instance, focusing on the first question, the computation is going to start with a state on the two priors. With state transformer, we're going to move it to the disease node. With state transformer again, we're going to move it to this node. And then we're going to do an observation of a positive test. And this is the conditioning of a state over a predicate. Okay, so this is pretty simple. Yes?
Zero conditioning is in the Python. So
Yeah, that's right. So the conditioning of A of omega over P. So suppose these are both on a set X. So this is for each X in X. You take the value of omega over X, you multiply it over the value of P over X, and you need a normalizing factor because this is usually how conditioning goes to make it a probability again. And the normalizing factor is the validity of P in omega, which is defined in this way. Yes, provided is non-zero. So this is a partial definition, as it usually is with conditioning. So when this is zero, this is undefined. Okay, and if you're asking about a categorical way of doing this, I would say we don't have a very satisfactory answer. So there are ways of making it a bit more categorical. There are a few also papers on that, but it's not very easy. It's not, I mean, the deep reason is that this conditioning doesn't cohere well with composition. It's not a compositional operation, so it's hard to make a nice general categorical definitions. But there are a few papers on that I can tell you later.
I just wanted to say quickly that this perspective of drawing string diagrams to visualize Bayesian networks, something that Brendan Fong developed.
Yeah, we acknowledge that.
Yeah, I know.
Yeah. Yeah, I could.
He knows that we.
Yeah. I could even go. I could even go farther and say. I mean, we essentially got started with this, looking at Brendan's thesis that tried to cohere with this effectus theory that was developed at Nijmegen at the time. So it was really one of our starting points. There was another question.
You answered my question, which is
okay.
it ontorial? And the answer is no.
Okay. Good. So let me just move on and show the calculation for this. So we work in this portion of the Bayesian network, and we first consider a state. To begin, we always need a state somewhere. This is a state over 2g times 2e. Oops. Then we use channels to transform this state as a state on 2 of t, okay, on the test node. And this was our notation, but this is simply composition in the Kleisli category. So we use channels T and D as state transformers. Then we consider now a predicate on this node, positive test. This predicate is simply a sharp predicate, meaning it gives 0, 1 values to the elements. So it gives a probability 1 to the event of a positive test. It gives a probability 0 to its opposite. And finally, the answer will be the conditional state given by this whole state conditioned over the positive test. And if you do this computation using these definitions and this one of conditioning, you find out that the answer is just the usual one if we compute with Bayesian probability. Okay, so this was the first computation. Let's make the second. So this one. Things here we got a bit more interesting because predicate transformers will also be involved. So we will start with a predicate now on this symptoms node. which expresses the observation of the symptoms. And we're going to use predicate transformation to bring it back here to a point where we can observe it. We're going to start again with a state, lift it through state transformer, and finally, because we find ourselves in the same node, we can put them together via conditioning. The next step will be performing a state transformer again and performing conditioning again. So you see that predicate and state transformer, they really work as sort of message passing device that allow you to bring information along the network to the places where you need it to be. How this was formally? So we have again our network. We put our predicate, as we said. This is again a short predicate. We now perform predicate transformation, which brings it from a predicate on the symptoms node to a predicate on the disease node. Now we do the conditioning, and finally state transformation. Okay. So we do the conditioning. Here we obtain again a state on 2D, and now we're gonna do state transformation on what we got. So you see here that state and predicate transformer, they can be nested and they can put them together any way I want. So here I'm doing first a predicate, first a state, then a predicate, then a state transformation again. Yes?
Is this related to the junction tree algorithm?
Yes, there is a relationship, and Bart is going to talk about it. He's going to talk about it in good detail, so I think you will be satisfied somehow. Yeah, maybe this is a good point to say it. All this can be. So this is a kind of different flavor with respect to the ways things are doing usually, and it can lead to algorithms inspired by different ideas. And so Bart is going to show you precisely one such algorithm based on this semantics, which has a relationship to the junction trees. You're going to see that. Yeah.
Say for inference of Kleisli, are you using the internal language or something, some hacks to set this up? I already know what Bayesian inference is. It seems that you're doing Bayesian inference and then saying that it's an error in Kleisli rather than constructing it using the abstract structure of that.
So what you mean is to define inference abstractly and then instantiate to the category?
I'm asking you trying to do it abstractly or not. Is that
I mean, so Bayesian inference is so what is abstract here is the toolbox you're using, and this toolbox looks very familiar in this category, but less familiar in other categories, as I said before.
have you given us the abstract definition of this toolbox?
Well, yes. I mean, a state is an arrow of this type. You can think of it in other categories as well. A predicate is an arrow of this type. You can think of it in other categories as well. A channel and so on. So
This summation, this is not very abstract.
yeah. So this doesn't work in all categories, but there are other categories in which it works, and there is work about generalizing this as well. I'm not going this direction, but this can be done to some generality. Okay, so yeah, we finally have the positive test, and the answer is again a conditioned state. Okay, looks like this is fairly clear. What I want to give is just a demonstration of how fuzzy predicates come in, because all the predicates we've seen so far, they are 0 to something, 1 to something else. No? So one could think, what is the need of fuzzy events at all? So this is the kind of a situation where an observation is truly associated with something fuzzy. So imagine, for instance, you want to compute the probability of a positive test given some information which amasses together, for instance, the feedback given by different doctors. One says that is 70% sure the patient manifests the symptoms, but there is another doctor saying is 50% sure that it doesn't. So you want to put all this together. This is contradictory information, but this happens in reality, right? So you would model this at this predicate, for instance. You see, this is a predicate which wouldn't be a state if you tried it, and now you can just redo the same computation using this observation instead. So this may look a bit weird, and this is indeed, I mean, this is the main point of contention when you show this to a person doing Bayesian probability in a standard setting, let's say. But really believe in it, and somehow when people talk about soft evidence, for instance, there is this concept around which persisted us for many years. People are talking about something which is very close to that. So this is an idea which is there, but people somehow are trying to model soft evidence many times using what we call states, no? So probability distributions. And we argue this is a more sensible way of doing it. And there are examples showing this even in finer details, which you can also find in the paper.
What's the idea of soft evidence?
The idea of soft evidence is that instead of evidence given by a 0-1 predicate, you have evidence given in a probabilistic manner, in this way. So this is soft evidence. The contention is whether soft evidence has to sum up to 1 or not. Yeah.
In this example, you've got Dr. Wallace 70% sure, patient manifests a certainty. So he doesn't. What if Dr. 2% sure he does? Then would you say S goes to 1.2?
Yeah, I would try to aggregate them.
Seems a bit.
I mean, this step in which you go from natural language to a predicate, this is I mean, this is subject to debate. But the point is, here you have the possibility, if you like, to have this more incomplete picture, more flexible picture.
Maybe you can also have to model it via two predicates and condition clause.
Yeah, this is another possibility. Yeah. And you can compose predicates together in a certain way. I mean, it didn't say this, but predicates and states, another reason to like them is that they have a nice algebraic structure, which is very different. So states over X form a convex set, and predicates over X form an effect module. So there are operations that you can use.
If you scale a predicate by a non-zero constant, does
Mm.
that affect anything?
Not if you use a conditional, but in general,
Yeah.
But for conditioning it doesn't.
as long as
So the absolute value
scalar
is
is
zero.
non-zero.
The absolute value is still that.
Okay. Yeah, I'm almost done. I just have 5 minutes. I just wanted, so enough for inference for the moment. I just want to give you an idea of what else this language can talk about. There are various directions. One I want to hint at is influence. So the two questions show the phenomenon which is very well known in Bayesian probability, namely that evidence of one sibling can influence the other sibling. Okay, so if I know something about symptoms, this will change the probability of a positive test and vice versa. And this can be said in our framework as follows. If I have a state which gives me the positive test, and if I have another state which is the same state by now conditional over something I observe over the symptoms, in general these two states will be different. So this is what influence means. Adding this observation changes the state of positive test. Now another phenomenon which you observe is that this influence can be blocked. How it gets blocked? So it gets blocked, for instance, if you do an observation on their common parent. So you have the disease node. Suppose you observe something about the disease. Then any further observation you will do on the symptoms won't change the positive test. So it used to change it before, but after you do this observation on disease, it cannot change it anymore. No? And this also makes sense intuitively, no? Because suppose I know the patient manifests the symptoms, I will change my mind over the fact that it's gonna test positive to the test. But once I know that the patient is sick, I don't care about the symptoms anymore. I know it's sick. I know this is going to influence the test anyways. So knowing that the patient is sick blocks any influence from this node to this other node. And this in our language can be expressed as follows. You see that this is the same expression as before. It's just now I do another observation on the disease node in here and in there. And this observation blocks the influence, meaning if I do this, Now I don't get anything different. Here I have an equality, where here I don't have it. And the nice thing about this language is it can make you, it allows you to prove such a statement, and it gives you some insights. For instance, you can prove this thing is true only if this observation is a sharp predicate. So if this event is of the form 1 to something, 0 to something else. If it's fuzzy, then this is not necessarily the case. Okay?
Is this a condition within it, which you've written down in the second equation?
Yes. Yeah. So what? Yeah. Well, in this case, yes, is in the, but there are other scenarios of this separation in which you simply talk about this separation. So when they are in serial, or when, for instance, they are there are two parents of a common node. Yeah. So in general, this is one case of influence, but you have other cases, and there is a sort of complete result about all cases of influence that you have in a Bayesian network, which is summarized by 3 disseparation scenarios, all the cases in which influence can be blocked, and we can prove these scenarios as formal statements. Another thing you can do, you can move from this setting to category of metric spaces, and keep our states with a notion of distance, which is there to represent, to quantify the influence that states may have on each other. Okay, and with these metrics, you can, for instance, do a further analysis about this separation and say the influence was bigger than 0, it gets reduced to 0, and so on. So you have a quantitative setting that is enabled by the categorical semantics to talk about influence. Okay, my last couple of slides is somehow a bridge to what Bart is going to talk about. So summing up, we have seen this predicate state transformer picture to revisit an inference in Kleisli of D. And this was based on the interpretation of our network as a string diagram that looks pretty much alike. However, you can also do a different kind of thing. Our Bayesian network, we can somehow flatten it and think of it as a big joint state with 5 pins, because we have 5 nodes. And the idea is that each of these pins represents a certain node of the network. Okay? So this is a sort of serialization of this same information. Once we have this representation, we can think about inference in a different manner. So when we have this, for instance, we can compute these inference questions as follows. We have our joint state, and we condition it over a big predicate, whose meaning is essentially other nodes, they stay idle, they stay silent, and the only node on which I make an observation is the test node. Okay? And then, as an answer, I want to get the 4th marginal of omega. So the 4th marginal is the marginal that corresponds to the test node, is this one. So this is another way of computing the answer to my question that uses a different representation of the same information. And for the other question, I have a similar way of doing the computation. You see that I have positive test, but I also now have another predicate, which is this one, which is now on the test pin. Okay? So one may wonder rightly whether this makes sense, in the sense, is this equivalent to what we were doing before? And the answer is yes. It is equivalent. So if I represent Bayesian networks in one way or the other, and I perform inference, I'm going to get the same result. But this is where Bart steps in. This can be made formally precise only once we formally understand the relationship between our joint distribution representation of the Bayesian network and its representation somehow as an atomized version in terms of channels. You can do a computation in Kleisli that makes this string diagram equal to this other string diagram. So you see, this is just the Bayesian networks where you put pins to observe each of its nodes. Okay, and this computation is what in Bayesian probability is usually called disintegration. So once you understand this integration, you can prove this equivalence theorem. And this is where I leave the word to Bart. Yeah, you can. So you get all the questions since I'm. Oh yeah.
Before Bart starts, let's steal this opportunity to write our first discussion topic.
Started, I have to wait. Thanks to Fabio for introducing the topic. What I will talk about is taking a deeper dive. Go deeper into this integration. There are a couple of papers underlying this. The first one was mentioned by Fabio already. This is a fairly recent one of mine about the new algorithm. And this one is together with a PhD student of mine, Kentak Joe, on this integration. Let me recall on an abstract level what Fabio has described. If you first want to do predicate transformation and then update the state, we'll write it like this. So you first do US predicate, omega is my state or distribution, probability distribution. I do predicate transformation, pull the Q backwards, and then update the state with it. This is what people in the Bayesian community, the logical sequence is otherwise. You can do it in this order. You can also first update the state and then do a forward state transformation. You get a new state and do a state transformation. These things have different names in the community. They are called evidential reasoning or explanation, or we like to call them backward reasoning. So you have a predicate reason backwards and then update. Or they're called causal reasoning or prediction if you go forward. If you first incorporate your evidence, your P, into your distribution, and then use it to push it forward to get a new distribution. And you can mix these two. And the idea is, what Fabio described, is that you can interpret a Bayesian network basically as a graph in the Kleisli category. And this graph is given by these channels, and along these channels you can move up and down with predicates and states and then follow a certain path and reason. How do you reason systematically, especially about bigger networks? Bigger networks within the order of 30 or 50 nodes, which contain lots of information, let's say about medical diagnosis, where you have many symptoms and many tests, and they may interact in various ways. Then it becomes interesting. The common starting point for inferences, you have several points of evidence. I have such a test, I see these symptoms on my patient. And then you want to focus on a certain observation, which is the conclusion you're trying to reach. There are standard algorithms for this. We basically know how to compute this. This is a big sum, multiplication, division in order to normalize things. But the question is how to do this efficiently, especially in bigger networks. Because things blow up very quickly, and you need to have a good strategy to keep size limited. I've used a standard implementation in Python in a package called pgmpy. I have a new algorithm which I'll sketch to you, which does both forward and backward inference. And after first what I call stretching the Bayesian network into linear form. Now, how does that work? The idea is if you have a Bayesian network, there is a way of ordering all the nodes in such a way that all the predecessors have already been visited. And there are many ways to order a network in this way. It doesn't matter too much, and there's a mathematical result in which way you do that. The stretching, I actually wrote in Python implementation for this, and also I'll show you some outcomes and get some nice pictures of this. As I said, the stretching is non-deterministic. You cycle through children of a node, and these children are organized in Python as a set and not as a list. So if you iterate over this, what comes out is every time differently, but that then doesn't matter too much. So this is the typical kind of Bayesian networks I'm interested in. There's a standard library called BNLearn, where they have many of these examples. And this is some medical thing. I don't understand what it is. The probabilities have been left out in this case. But as you can imagine, this blows up very quickly. So what is the kind of inference you want to do? I have some information here and there, and maybe also there, and I want to understand what is the probability of this. Now, how do you go up and down your network? Now, what predicates and state transformation, there are different paths to follow. And the trick is how to do that in these inference algorithms. Now, how to stretch such a network to make it linear? Let's try this. Well, we start here. This one. Which one can we do next? We can choose this one, because we have all its predecessors. We cannot choose this one, of course, but next we can do this one. We keep this one. Let's go. We can do this one, this one, then this one, etc. There are different ways of making them linear, as long as you do this in such a way that all the predecessor, the back nodes, have been visited. Here's the same one, again made smaller, and this is one way of sketching it. It is in principle linear, but the drawing package doesn't draw it linear. It puts things side by side, but I guess you can see a certain order in this here, how to do this. Still, certain things are done in parallel. And another way of sketching it is written here. Where's the difference? Well, one thing I changed in these networks is that I made the copy nodes explicit, just like Fabio did, and that's very important for a categorical representation. And you see, if you look at the copy nodes, you can see already that the stretching is done differently. And also you can see, hopefully intuitively, the copying is done in a lazy way. I copy only at the moment when I really need something to keep the size of the network limited. Because this node is used many times, but I only copy it when I really need it. So here the copying works in a different way. Okay, so question?
I was expecting that to look something like a total order looking at this transformation. So what is this?
Yeah, it is a total order, but it's the drawing package that makes it. It does not make it a drawing, a linear order.
Oh, okay. So,
It's a.
So all of these things have a kind of number.
Yeah, that's precisely.
It's just there's some independencies.
Yeah,
still.
Yeah. But also, otherwise the drawing would become extremely long. So let's look at this at a more abstract way. So I have an initial node and a final node. I've ordered my network linearly, all these nodes, and these arrows here, they involve some parallel identities. I have to copy state a lot. And so I have some evidence nodes, as I said. I have several points of evidence, and I have a point of observation. And this is, there may be multiple points, but I took two. But the interesting thing is that the observation may be after the evidence or also before some other evidence. Now, how to reason with this? The algorithm works as follows. I start doing state transformation here. So I have an initial state, I do state transformation, basically Kleisli composition. Again, hey, here I have some evidence. I update my state, and I continue with state transformation, etc. I stop here. Okay. Next step is I start doing predicate transformation. I start here. I go backwards, do predicate transformation. Hey, I have some evidence. Okay, I do conjunction with the evidence with what I already have. Go backwards, stop here. At this stage, I have both a state from here and a predicate from here. You guess what I'll do? I'll update and then output. So update the state that you get from here and with the state and the predicate from here. And as you can imagine, this maybe if I do a different stretching, both evidence. A piece of evidence maybe here, or even both maybe here. So there is a correctness result needed that the outcome doesn't depend on the form of stretching. Actually, it doesn't. I don't have a mathematical formulation of it here, but if you're really interested in it, I refer to the archive report, where it's mathematically proven that this does not give the outcome. Okay, I can do, maybe I'll postpone the demo to the end. Well, no, I'd like to do briefly show it to you. So what I'll run is a program now in parallel. So this is the network, and I run it 10 times. The first times printed here are for variable elimination, which is the standard algorithm, and this is the new algorithm. And in the end I compare, and how much faster is this stretch and infer that I'm using than standard. Variable elimination is 10 times faster, which I think it's interesting. It's purely theoretical work which leads to this algorithm, which is really faster. Now it's highly non-deterministic. If I run it again, oh. Now it's 40 times faster.
You find examples who's really killed this out?
In what sense kill?
How you, it could be this particular Bayesian network has some
That's
kind
true.
of sparseness that makes
That's
it
good.
work really well.
That's true.
Have you figured out ways?
No, I've tried many. Suddenly mine is 58 times faster. So it's, I mean, that's. But what's interesting if you compare a little bit, the times my algorithm use are fairly constant, but it's really variable elimination or algorithm that varies a lot in the time it uses. So my approach was rather constantly. I'll switch on a rather big example just to give you an idea.
Can I just ask,
Sure.
that was always with the same linearization, those three rounds, or
No, no.
independent linearizations that could be different?
Yeah, I choose a different inference set each time. So I'm now running this, an inference query on this one, and I actually printed the query. So this is the observation node, and here's a list of evidence nodes. I have 3 evidence nodes, so maybe you can find it if it's a good student. I have this information, etc. And you see, this is the outcome, the home-based distribution. It contains 4 elements, and it printed it within a second. It's now running variable elimination. And you see, this can easily take an hour. It can also finish in 10 seconds, the next 10 seconds, I don't know. But my experience is the bigger the algorithm or the network is, the better my algorithm works up to a point. If you sometimes this runs out of memory on my computer, so I need a bigger machine to do this. But at a certain point, so I've tried this out on a big machine at the department, which has 3 terabytes memory, I think. And on examples 3 times as big, it also runs out of memory. So really, it blows up very quickly. But I would say the conclusion is that this approach is certainly competitive. And what I definitely like about it, it comes really from abstract theory, so it's a good example of applied category theory in this conference that leads to new algorithms. I'll kill it. No, I haven't done none of that. So the archive report I've been referring to describes the semantics, and it has a short paragraph for comparisons, performance comparison, but nothing systematic. That still has to be done. But I'm sure it will be difficult because it's so deterministic what's going on in this area. But a new challenge. Yeah? I can keep it running and maybe at the end of the talk see if it has come back. Well, I hope it doesn't freeze my machine in the meantime. Yeah, that's a risk. So this integration. So Fabio has already talked a bit about graphical languages. I guess most of this is familiar. What I would like to point out here is that if we have a state with 2 pins, marginalization is written in this way. You really stop one pin, or you stop it like this. And channels have this property. If you stop the channel, then you might as well stop everything. We do have copy nodes which satisfy these nice diagrams. In general, copying is not natural in a deterministic setting, in a probabilistic setting, unless you have deterministic maps. And what are the main examples of categories? Kleisli of the distribution monad, of the jury monad, various variations on this, but actually also the power set monad, non-empty power set monad was an example of this. Let me come to this integration. This integration is a very, very interesting topic. I've been working on it for maybe 2 years now, and it applies to joint states. And what it does, it extracts a channel from a joint state in a very special way. And it does it in such a way. So a disintegration of a state on x and y is a channel from x to y, such that the whole joint state can be obtained in this way. So I stop one channel, but I reconstruct it. Sorry, I stop one pin, but I reconstruct it via this channel from the other one. This is really, really a very basic operation. They may not exist, but what I wanted to point out is that what this expresses is this formula for conditional probability. So the conditional probability here is probability of y given x. That should be read as a channel from x to y. And then this dot is the copying that's going on here, because we need x twice. So here is the copying here, and this expresses that the joint state omega x comma y can be written as a multiplication of this in this way. Now, why is that a very basic operation? At the end of his talk, Fabio sketched that a joint state, right, a Bayesian network, can be described either as a joint state or as a graph. Now, this integration is the way to extract a graph from a joint state. If you have a joint state with many pins, this integration is the way to get the graph structure. Now, this is only in binary form, but you can generalize this. If you have n pins, you can disintegrate from each subset to another disjoint subset. And that gives you a channel. And in this way, you can iterate this and get a certain graph structure from a joint state. So it's very, very, very important.
Can I just ask a quick question? So when you have some zero probabilities, I can see that disintegration may not be possible.
That's true.
But is there any other reason why it might not be possible?
That's the main reason. That's the main reason. But in a continuous setting, all of this becomes much more subtle. Yeah.
Finitely, zero probabilities isn't a problem of existence, right?
Yeah, with uniqueness. So you can give an arbitrary definition, and because you have to multiply with zero, and whatever you fill in makes the equation, satisfies the equation. in this precise mathematical form. There's a sort of dual version of it. If I update in the second coordinate with q, then marginalize in the first coordinate. What I can also do is update the first marginal with q directly, and then do state transformation along this channel. So instead, here I do predicate transformation, here I do state transformation. So both fit with the operating on the joint state. Now, as you may remember, in the beginning I called this backward inference. First predicate transformation, then updating, and forward inference was first updating and then state transformation. So these two basic forms, they can be described on the joint state as well. This extends to multiple form where you take the fourth marginal like Fabio did, but this is really the essence. Okay. Yeah, and we like to call this crossover inference. Because you cross over from one coordinate to the other. That's how you do inference there. Okay, I have some more applications of disintegration. If the chairman allows me to take 5-10 minutes. More like 5 than 10. Okay. Conditional independence can be expressed via disintegration. I'll give you the intuition showing some pictures. Conditional independence of x and y given z is usually expressed by this equation. Now these are channels, right? From z to x, from z to y, from z to x comma y. So this involves disintegration. Let's try to make this explicit. Again, this is the equation we want to express. The left-hand side is given simply by this integration from z to x comma y. I'll show it in a minute. The right-hand side is more interesting because you have this integration from here from z to x. How is it obtained? Well, first of all, you see that the y is no longer there, so we marginalize out the y, and we do disintegration with respect to these two pins. So x, the x part is reconstructed from z. That's what this said, from z to x. The same way, x is no longer here, so this one disappears. We have two pins, and we reconstruct the y part from z. So we go from z to y. Okay. That's how you get these channels. Now, conditional independence can be described pictorially as this. So we have our joint state like this. It can be described on the right-hand side, left-hand side, like this, from z to x comma y. So both x and y are reconstructed from z. This is equal to this. So basically what you say is that this channel from z, given z, x comma y, is obtained by copying here the z. You see the z occurs 2 times, and then as an multiplication. So it's a nice graphical description of what's of a very fundamental concept. What's Bayesian inversion? Bayesian inversion is an operation given a channel like this and a single state here, is a channel in the other direction. Again, it need not always exist, and there are various side conditions, but if it exists, it behaves very nicely. The property is this. It's a special case of disintegration. Basically, you disintegrate this joint state, and then this is the channel you pull out, and this is the equation that satisfies. I'll show you. I'll use that as my last example, because this is applied category theory. It's good to have another example. This is a standard example from the literature. This book, Witten, etc., is a book in data mining. And this is a big example they have in there, sort of their running example. You get such a table, right? Lots of data. And the question is, given this table, and given that we have a sunny outlook, cold temperature, high humidity, and windiness, what is the probability of playing? So how do you go about this? And so what does this table give you, and how should I now derive probabilities for these new events? Right? Given these circumstances, they don't really occur in the table, but how should I do it? Well, theory is very useful here. The book simply contains concrete calculations, and then they suddenly say, bang, this comes out, and I mean, I'm surprised how precisely they do it. How I do it is I take this, turn this into 4 channels. I'll describe in a minute how I'll do this, but I'll extract those via disintegration from the table. Given these 4 channels, I can form a tuple of channels. I copy, and now I disintegrate this. Now remember, disintegration gives you a channel in the other direction. The inputs were precisely these things. I had, what was it, sunny outlook, high temperature, etc. And by disintegration, I get a channel in the other direction, and I can compute the other. This is naive classification for people who are in the know, who ignore all possible dependencies in the table. You simply assume there are these dependencies, but that works surprisingly well in practice. So how do you do it? Turn the table in a big joint distribution. Extract channels via disintegration. Use inversion for this classification task. So the joint distribution, you take it on this product state of outlook, temperature, etc. These have three elements, temperature, I don't know, 2, or etc. You get a big Cartesian product. And each of the listed combinations, you give a 1/14th probability. Because there were 14 occurrences, you give a uniform distribution. So you have a joint distribution, you extract these 4 channels out of it, and then you go about calculating your inversion with these inputs. Again, we have some tools for doing this, because by hand it's a pain. But you get an outcome of 20.5%, which is precisely the outcome that Witten also calculates in a way that I don't understand. I do understand the theoretical way of doing this.
I think he uses string theory or something.
Yeah, he must be. I'm sure. He doesn't want to burden his readers with it. Actually, the inversion also works for the continuous version that's in this book, but I won't. So I'll skip I'll do it. I'll see if he kills me. Natural. I'm sure you want to see this. This is also a nice example. I don't know if you've seen this in natural join. It's an operation that occurs in database theory. If you have 2 databases and you want to join them together, what is the example? Suppose in both databases you have students. One you have students and marks, student numbers and marks, and the other one you have student numbers and addresses. You want to merge them somehow. That's the idea. There is a column that they have in common. How to do this? There is a join which is written in such a funny bow tie, which is defined then in this area. Now, how to do this? I'll focus on the pictures. So what you have 2 databases, omega and rho, and they coincide on one column. So if I throw away the addresses and I throw away the marks, I keep students in both cases, and they coincide. What I'm looking for is a bow tie, a ternary state sigma, which marginalizes to both. So sigma is 3 pins, and if I leave out this one, I get omega. If I leave out the middle one, I get rho. How to do this? This is a big topic. There are various algorithms in the literature for doing this. The solution by disintegration is very nice and simple. So the assumption I have is that these marginals are the same, and I'll write them as tau. Now I use this tau to obtain 2 disintegrations of omega via C and of rho via D. Now how do I get my ternary state? Well, once you've got this point, it's sort of obvious. Given this tau, you copy it twice. This is your ternary state. If you now delete this one, you keep these 2 pins, you get rho. If you delete this one, then you get this one, which is odd. So by construction, it marginalizes to both. What I will skip is some example with some running code in Python, which really does that. And I'll leave you to read my conclusions. That's it. Thanks.
Okay, so because we started a little bit late, and now we're about 30 minutes, I suggest we do the plenary discussion now until, say, 12:05, and then go to the short meeting.